Well, as promised, you had to work quite a bit on that previous problem on local area networks. We're now going to give you a rest with an extremely simple added problem in the area of separation between antennas. This is Chapter 7 of this tape. The problem states that microwave towers are 100 meters high. It asks you for the maximum distance between antennas. What's not stated in the problem is that we're really asking you for a best case situation. You have to assume that there are no obstructions between antennas. Well, the limiting factor in spacing between antennas is the horizon, the curvature of the Earth's surface. We are looking for the line of sight distance between two antennas. Well, you have a couple of choices here. If you're a whiz in geometry, you can draw a circle, draw two little antennas on that circle, and see how far apart they can be before the line joining them has to go through the surface of the Earth. I would suggest you find the appropriate formula in one of your references. The formula is that the distance is 2.9 times the square root of 2 times h, where h is in meters and d is in kilometers. Well, we simply plug in the height given in the problem and solve to find an antenna separation of 41 kilometers. This is one of the choices in the problem, so the correct answer is selection C. And that concludes this very simple problem. I'm now going to walk you through the third of the problems from your workbook, a multiple choice problem. This will be problem 597 that appears on page 108 of your workbook. This problem is a kind of hybrid that deals more with electronics than with communications. The reason it's classified as one of the communication problems is because the application is typically in fiber optic communications. So what we're going to do now is Chapter 8 out of the 14 chapters on this videotape. The given circuit begins with a signal that's fed into an AND gate. Because the two inputs of the AND gate are tied together, the gate is being used to condition the signal. The signal coming into the gate is a 10 microsecond pulse with a 100 microsecond period. This means it's a pulse train with a 10% duty cycle. The output of the AND gate, this point G, is a pulse train of height 5 volts, pulse duration 10 microseconds, and pulse period 100 microseconds. That goes into the gate of the field effect transistor. You're told that the gate to source voltage, VGS, of the field effect transistor is 1 volt when the transistor is on. In this output loop, we also have a photodiode, and you're told that the voltage across that diode is 1.5 volts. You have a variable power supply. It's a DC supply that varies between 10 and 30 volts, and you have a 10 ohm resistor in the circuit. I show the equivalent circuit of the FET here. Here's the original circuit up here. Solution of this problem does not really require much knowledge of field effect transistors nor of photodiodes. I present the equivalent circuit for the transistor when it's on just so that we can observe some things about this. Note that the FET is a voltage-controlled device. The output current between drain and source depends upon the input voltage, the gate to source voltage. And in fact, it's equal to G sub M times VGS. If you look at the input loop, and I've shown this when the pulse train is positive at 5 volts, looking at this loop, you have 5 volts at the input, You have 1 volt as the given voltage between gate and source, so you can easily find with a loop equation that the voltage across this resistor is 4 volts. The first of the 10 parts of this problem asks you what happens to the voltage across the resistor as the variable supply goes from 10 to 30 volts. So you're asked for the voltage across this resistor as this varies from 10 to 30 volts. And you're given 5 possibilities. We look once again at the equivalent circuit. So we're saying this supply goes from 10 to 30, and we want to know what happens to the voltage across the resistor. Well, if we look again at the input loop, when the transistor is on, when the pulse is high, we have 5 volts here. We're told that VGS is 1 volt, so all we have to do is sum voltages around this input loop. We find V sub R, the voltage across the resistor, is simply 5 minus the gate to source voltage for the FET, which is given as 1. So we get 4 volts across the resistor, and this is independent of the value of this variable supply. So the correct answer to this question is C, that the voltage across the resistor remains the same. The second question asks what happens to the resistor current when the variable supply is reduced from 20 to 10. So the problem wants you to talk about the current through this resistor when this variable supply is reduced from 20 to 10. And again, you're given 5 possibilities. Well, we really don't have to go any further than we did in the first problem. Because the voltage across the resistor is independent of the supply voltage, we found the voltage across the resistor was 4 volts whenever the transistor is on. The resistance is not changing. So Ohm's law says I equals V over R, and that won't change. If the voltage doesn't change, the current doesn't change. So the correct answer is E. The current remains the same. Well, hopefully you're getting the idea at this point. The third of the 10 parts asks about the output power of the LED as the variable supply is increased from 20 to 30. In other words, now the variable supply is going from 20 to 30, and we're asked about the light output power from the LED. We're given 5 choices again. Well, this is sounding like a broken record, but let's repeat it again. The voltage across this resistor stays at 4 volts. So the current stays at 4 divided by 10. The current is constant. This is a single loop, no connections for current to escape from this loop. So the current through the resistor is same as the current through the diode. So the current through the diode is not changing. It's independent of this supply. Well, if the current through the diode remains the same, the light output power remains the same. So the correct answer to this part of the problem is A, remains the same. Well, I've repeated the equivalent circuit here. I know it's quite small on your screen, but we just want to see the overall layout. We're asked about the power in the FET. Remember, the current remains constant. The current in this output loop is simply determined by the voltage across the resistor, which is constant at 4 volts, independent of this variable supply. So the current is a constant. The power in the FET is the product of voltage times current. And so if we look at the voltage across the FET, that's going to give us the necessary information to see what happens to the power. This voltage is found simply by going around this loop, summing voltages. So the drain to source voltage is the variable supply voltage minus the voltage across the diode, 1.5, minus the voltage across the resistor, which we know is 4. So we get that the voltage from drain to source is the variable supply voltage minus 5.5. Now let's look at the 2 extremes. When the variable supply is set at its minimum of 10 volts, VDS, the voltage across the drain to source of the FET, is 4.5 volts. When the variable supply goes up to its maximum of 30, the drain to source voltage is 24.5. So the ratio of powers is simply the ratio of the voltages, because the current is constant, which is 5.44. That means as the variable supply increases from 10 to 30, the power goes up to a factor of 5.44 times the minimum power, which represents an increase of 444%. You scan the possible answers in this multiple choice problem, and you find the closest one is C, increases by 450%. Question 5 asks about the power dissipated in the resistor during a complete period if the duty cycle is doubled. So notice the on time goes from 10 microseconds to 20 microseconds. So the duty cycle is going from 10% to 20%. And we want to know what happens to the power dissipated in this resistor. Well, the power in the resistor is constant whenever the transistor is on. Remember, whenever the transistor is on, there's 4 volts across this resistor. So the power is simply V squared over R, and that's a constant. When the duty cycle is 10%, the transistor is on 10% of the time. So the average power is 1/10 of V squared over R, the power when the transistor is on. When the duty cycle doubles to 20%, the average power is 1/5 of the power when the transistor is on. So clearly, the power doubles when the duty cycle doubles. So the correct answer is D, the power increases by 100%. Well, now you're asked for the minimum average power dissipated in the resistor during a complete period. Well, once again, the resistor voltage, the voltage across this resistor, is 4 volts whenever the transistor is on. So the power when the transistor is on is V squared over R, or 1.6 watts. With a 10% duty cycle, the average power is simply 1/10 of this, or 0.16 watts. This is selection D on the possible answers. Question 7 is a very simple question. You're told that the value of the variable power supply is 10 volts, and you're asked for the voltage drop across the FET. You're told this is 10 volts and you want the voltage here. We've really already done this as part of a more complicated question. The voltage drop across the FET is found just from a simple loop equation here. You've got the voltage across the FET, the voltage across the resistor, the voltage across the photodiode, and the source voltage. So the voltage from drain to source, the voltage across the transistor, is simply the supply minus the diode minus the resistor. When the supply is 10, this leaves 4.5 volts across the transistor. So the correct answer is E, 4.5. Question 8 requires putting together some of the results of the previous questions. You're asked for the minimum average power dissipated in the FET, not the resistor, but the FET, during a complete period. Well, so we're looking at the power in the FET. Remember, the current is constant throughout this process. So all we need is the voltage across here to find the power. As in question number 6, the current is 0.4 amperes. In question number 7, we found the voltage drop was 4.5 volts when this source is 10. And since we're asked for the minimum power, we want the minimum value of this source. Remember, the larger this source, the larger the voltage drop across the FET. So to find minimum power, we use minimum source value. So the power dissipated in the FET when it's on is just the product of current times voltage, and we get 1.8 watts. Since the duty cycle is 10%, the transistor is on 10% of the time, so we take 1/10 of the on power and we get 0.18 watts. So the correct answer is part E, 0.18. Well, question 9 is the same as question 7, but for a different value of voltage supply. You're asked for the voltage drop across the FET when the supply is at its maximum, 30 volts. Once again, all we're going to need is a loop equation, summing voltages around that loop. So now we're setting the variable supply to 30 volts, and we want to know the voltage across the transistor, the drain to source voltage. We've essentially done this problem when we looked at the power dissipated in the FET. All we have to do is go around this output loop. You know the voltage across the diode, you know the voltage across the resistor, you know the variable supply voltage, and so you simply find the voltage across the transistor. The drain to source voltage is equal to the variable supply voltage minus the voltage across the diode minus the voltage across the resistor. 30 minus the diode voltage is given as 1.5. The resistor voltage we know stays constant at 4, so we get 24.5 volts. Looking at the choices for the answer, we find E is the correct selection. The last question is very much like question number 8, but instead of asking for the minimum average power, it asks for the maximum average power. So the only difference, we now need to raise the supply to its maximum value, because that will give us the maximum drain to source voltage. Okay, with the 30 volt supply, the voltage across the FET is 24.5. You could either simply do the loop equation or look back at question number 9. The current is always 0.4 amperes whenever the transistor is on. So the power when the transistor is on is the product of voltage times current, or 9.8 watts. Since the duty cycle is 10%, the average is simply 1/10 of this, or 0.98 watts. So the correct answer is C, 0.98. So I hope you realized by going through the 10 parts of this problem that you didn't really need an extensive knowledge of FETs or of photodiodes. This was a relatively simple problem to solve. Well, now we've walked our way through the solution of 7 problems, and it's time to take a short break away from the solving of problems. This very short chapter presents some of the basic principles of broadcast AM, broadcast FM, and television. Some of these principles can creep their way into multiple choice problems dealing with more complex systems. This slide defines the various frequency ranges. As higher and higher frequencies are utilized, additional definitions are needed. We start with very low frequencies, VLF, and work our way through to extra high frequencies. Note that each term applies to 1 decade of frequency range. Well, we'll talk about AM radio. The band allocated for AM radio in the United States extends from 545 kilohertz to 1605 kilohertz. You might hear this quoted as 550 to 1600, and it's all a matter of whether people are talking about the extremes of the band or the assignments of the carrier frequencies, which are in the middle of each of the frequency allocated bands. Each station is allocated 10 kilohertz of bandwidth. The system utilizes double sideband transmitted carrier. It uses transmitted carrier so that we can use an envelope detector to demodulate the signal. That makes it much simpler and less expensive to build a receiver. The IF, intermediate frequency, used in standard broadcast is 455 kilohertz. And I show here a block diagram of an AM receiver. I know it's a little hard to see the details here, but I just want to talk about the overall operation. The signal comes from the antenna, goes through a tunable RF filter. It's tunable because you have to reject the image station. The process that's used to shift the frequencies into the passband of the IF filters creates a second frequency known as an image. We then typically have some RF amplification, radio frequency. We then multiply by a local oscillator, and that's what shifts all frequencies up and down by the frequency of the oscillator. We then go through the IF strip. These are simply typically 3 tuned IF filters that combine amplification and sharp bandpass filtering. We then demodulate with an envelope detector. We do some audio amplification, and we're ready to listen to the signal. Well, let's talk about frequency modulation, FM radio. Here the band is considerably higher in frequency than the AM band. The FCC allocates 88 to 108 megahertz. You might be aware that this is right in the middle of the TV band, television. Each station is allocated 200 kilohertz instead of just 10 kilohertz, 20 to 1, FM versus AM. The frequency deviation is 75 kilohertz. You may be aware that the higher the frequency deviation, the more immune to noise is the FM signal. The IF frequency used in FM receivers is 10.7 megahertz. The maximum audio frequency permitted is 15 kilohertz, as contrasted with 5 kilohertz used in AM radio. What about FM stereo? FM stereo transmits 2 separate audio signals in the same channel. Those 2 signals, instead of being the left and the right, are the sum and the difference signal, so-called matrix operation. This was done because in the early days of FM stereo, people who did not have a stereo receiver wanted to listen to the sum of the left and the right channel instead of just either the left or the right. The difference signal is transmitted on a subcarrier of 38 kilohertz, so that the 2 signals are multiplexed, the sum and the difference signal, with the difference being shifted up to 38 kilohertz using this subcarrier. A pilot carrier of 1/2 of this, 19 kilohertz, is transmitted to help the receiver demodulate the difference signal. And additional possibilities are possible in the FM stereo system. You can do more than 2 signals. You have space for more, and subsidiary carrier authorization, SCA, is transmitted on a subcarrier of 67 kilohertz. This is the traditional Muzak that's sometimes heard in doctors' offices, and also increasingly it's being used in paging systems. Also has other specialized uses. Power companies sometimes use it for demand subscription service to turn off people's appliances in a power emergency. Traditional television, analog. Well, the NTSC standard is 211,000 picture elements divided into 495 visible lines, 426 elements per line. So if you take the product of these two, you should come up with 211,000. There are 60 fields per second. In other words, the standard television scans from the upper left to the lower right. Actually, it's from the midpoint, but you can think of it as the upper left to the lower right, 60 times a second so that your eye does not see flicker, but it only transmits 30 separate full images or frames per second. This is what's known as interlace scanning. where in the first 60th of a second, the odd number lines are transmitted, and in the second 60th of the second, the even number lines are filled in. This is as opposed to progressive scanning that many computer monitors use today. Well, what's the future of television? And I'm saying very soon because as you view this videotape, most of this is already a reality. We're moving toward digital television, higher quality, more possibilities, inserting additional signals in the same channel, and some of the advances in data compression have really had a very positive effect on digital television. Interactive television, where television becomes a two-way medium. High-definition television. When television was first invented in this country, nobody envisioned using it as a universal communications tool. They never thought you would have to put text on the screen, for example. And so the original standards, the number of picture elements and the way color is done, makes it very, very difficult to transmit detailed pictures. In fact, in this videotape you're watching, we've had to avoid red as a color because of some of the shortcomings of traditional television. Flat screen TV. Traditional televisions use a scanning technique with a cathode ray tube where you're bending a beam of electrons to illuminate parts of a screen. Well, with computer control and various ways to display images, we don't have to do that anymore. We can scan an entire picture electronically by selecting which picture element we want to display. And finally, some things are being done today, experiments with holographic TV, which would lead to three-dimensional television in the future. Your booklet of sample problems does not contain any questions dealing with digital communications. Since this is such an important area within communications, I've added this problem on calculating error rates in a digital communication system. It's a very simple problem, but it'll give you some idea of the kind of things you might be asked on the exam. So this is Chapter 10, the added problem on digital error calculations. The statement of the problem is as follows. You're asked to find the probability of error of an incoherent detector. Detectors can be coherent, keep track of phase and timing, or incoherent. Much easier to build, but they do not perform as well as coherent detectors. You want the probability of error when it's used for FSK, frequency shift keying, where the bit period is 2 milliseconds. So we're transmitting 500 bits per second, and signals have an amplitude of 0.4 volts. You're told that the two frequencies used for the FSK are 100 kilohertz and 101 kilohertz. And you're given the power of the additive noise. We assume the additive noise is white Gaussian noise, and you're told it has a power of 0.01 milliwatts per hertz. So for each 1 hertz bandwidth, the power of this noise is 1/100th of a milliwatt. You're also asked to find the performance of the coherent detector, so you can compare the two. Well, as we solve this, we know the bit rate is 500 bits per second. That's given in the problem. Once you're told the bit period, the bit rate is simply the reciprocal, 1 over that. Note that the frequency separation is twice the bit rate. This is important because that separation represents what's known as orthogonal tone spacing. The spacing between the two frequencies does affect the error performance, and normally we do shoot for orthogonal tone spacing. Well, what we're going to need is the signal-to-noise ratio. The signal energy is simply the signal power, a squared over 2, the power of a sinusoid, times the period, t. So what you've got is 0.4 squared, that's the amplitude squared, times 2 times 10 to the minus 3, the period, divided by 2, which gives you a signal energy of 1.6 times 10 to the minus 4th. The signal-to-noise ratio is simply this quantity divided by the noise power per hertz, or 16. 16 translates to about 12 dB. Now, there are formulas to plug into to find coherent and incoherent performance. But I think it's far better to look in your references to try to find a pair of curves. Then it's a matter of simply going in there with the given signal-to-noise ratio and simply reading off the probability of error. Makes the problem trivial. You don't have to go through any calculations. Well, what we read from this chart is the coherent detector has a bit error rate of 10 to the minus 5th. That's on the average 1 bit error out of every 100,000 bits that are transmitted. The incoherent detector has a bit error rate 9 times as high. So you'd have to have a good reason to use the incoherent detector. Perhaps your problem specifications did not require a very small bit error rate, or your budget to design the system did not permit the extra hardware needed to do a coherent detector. Well, calculation of noise floor was part of problem 596 that we did earlier on this tape. We've added this simple problem we're about to do to emphasize the importance of this type of calculation. So we're on chapter 11 now, noise floor calculation. A multiple choice question that asks what is the noise floor of a 75 kilohertz bandwidth channel at 200 degrees Kelvin. And you're asked to assume that the signal is transmitted using a 75 ohm coaxial cable. 5 possibilities are given. Well, all we have to do is go to the equation for the mean squared noise power. That's 4kTRT, the difference in frequencies, and the units are volts squared. We need Boltzmann's constant, we need the temperature in Kelvin, we need the resistance in ohms, and we need the noise bandwidth in hertz. Well, when we plug that in, we get a value of mean squared noise, which is 6.21 times 10 to the minus 14th volts squared. Well, we want an answer in dBmV, so we calculate an RMS, root mean square value. That simply means take the mean square and take the square root of it. We take the square root, convert it to millivolts. In other words, 10 to the minus 7th divided by 10 to the minus 3 is 10 to the minus 4th. So we have 2.49 times 10 to the minus 4th millivolts RMS value. Converting this to dBmV, we simply take 20 times the log. Note it's 20 because we're dealing with voltage level and not power level. That gives us minus 72 dBmV, which matches selection E in the problem. Again, a very, very simple problem to illustrate just one point. Well, we're on the home stretch here. We're on chapter 12 of 14 chapters. If you look at your sample booklet, you'll see that it doesn't contain any questions covering analog communications. So I've added this very simple problem that deals with FM bandwidth. The problem states that a wideband FM signal has a frequency deviation of 300 kilohertz and a carrier of 100 megahertz. You're asked for the band of frequencies occupied by the FM waveform, and 5 possibilities are given. Because the carrier is 100 megahertz, it's a good idea to scan these answers to make sure they all have a center at 100 megahertz. You can reject any of them that don't. For example, this first one is not centered at 100 megahertz. Bandwidth is approximately given by twice the sum of 2 quantities. This is known as Carson's approximation. You add together the frequency deviation and the maximum frequency of the audio. So delta F is the maximum frequency deviation, the maximum amount that the instantaneous frequency of the FM wave moves away from the carrier. F sub m is the maximum frequency of the audio or the information signal in general. Now the signal is called wideband if the frequency deviation is much larger than the maximum frequency of the audio. So if the frequency deviation is large, the bandwidth is approximately 2 delta F. We dropped the second term to F sub m because we consider it to be negligible. Thankfully, this problem stated that the signal was wideband because we weren't even told the value of F sub m. A signal is narrowband if the reverse is true. If the frequency deviation is small compared to the maximum frequency of the information signal. So when a signal is narrowband, the bandwidth is approximately 2 FM. Incidentally, that's the same bandwidth we would have with double sideband AM. Well, since the given signal is wideband, the bandwidth is approximately twice the frequency deviation, or 600 kilohertz. So we have a bandwidth of 600 kilohertz centered at the carrier, so the range of frequencies is from 300 below to 300 kilohertz above the carrier frequency. Scanning the answers, the correct choice is C, 99.7 megahertz to 100.3 megahertz. The final added problem is a very simple multiple choice question about equalizers. We answered a similar question as part of problem number 596 earlier on this tape. Here, we spotlight some different characteristics of equalizers. We're asked which of the following statements is most correct about equalizers. And we're going to go through these choices individually. We have 5 possible choices. Notice the last one is none of the above. So if you don't think A, B, C, or D are correct, then you would choose E. Well, the first one says an equalizer has one fixed setting for all possible channels. Well, this is incorrect, since the equalizer function must change depending on the channel characteristics. That's the whole purpose of an equalizer. Second possibility, B. An equalizer compensates for the flat loss in a channel. Let me remind you that flat loss is the attenuation in all channel components except the cable. Well, this choice is wrong because the flat loss does not require an equalizer. It does not cause distortion, although an amplifier might be used to cancel the effects of flat loss, certainly not the use of an equalizer. C states that an equalizer provides a frequency response that is the inverse of a channel attenuation, which increases with increasing frequency. Well, this is certainly a correct statement of the goal of an equalizer. It's almost like the definition of what an equalizer is. Let's continue to make sure C is the most correct possibility. D says that an equalizer corrects for the variation in an amplifier transfer function. Well, this is wrong since the equalizer is configured to match the channel, not the amplifiers. Well, finally, E says none of the above. This would not be correct because we already found that C is the correct answer. Congratulations! You've made it through 13 chapters of this videotape. What we'll do now is briefly review what we've covered. So what have we learned in the last couple of hours? We learned about the examination format, various logistics issues surrounding taking the PE exam. We've done some examples of network calculations, gains and attenuations. We've done a simple problem involving cable loss. We've worked with local area networks without having to know a great deal about how they operate. We did a very simple problem involving the minimum separation between antennas. We did a problem with basic optical communications, although it was more of an electronics problem than a communications problem. We reviewed some principles surrounding commercial broadcast transmission, AM, FM, and television. We talked about calculating bit error rates in a digital transmission system. We did some noise floor calculations. We did a problem finding FM analog bandwidth. And we talked about equalizers several times during the course of this tape. Well, what should you do now that you've gone through this tape? My advice is that you put away the solutions and your notes from the tape and you try to resolve the various problems. Then you should make up your own problems. You know, my students do better on exams if they try to anticipate the kind of questions I'm going to ask. It's not as difficult as it may seem. Then I would suggest you watch the tape again and add a bunch of notes to the workbook, to the copies of all the slides as you go along. And study the other topic areas covered on the exam. Certainly the problems we've done do not cover all of the areas in the outline I gave in Chapter 1. And finally, go off and pass the exam. So in the introduction to this tape, I told you that my hope and expectation is that this exercise would significantly increase the probability of your passing the PE exam. I hope you will agree that the time you have spent with me was time well spent, and that indeed you now stand an increased probability of passing the PE exam. Thank you.